Look down. Beneath the thundering weight of a modern locomotive lies a secret, hidden in plain sight. Millions of jagged gray stones. A sea of rubble stretching across continents, from London to Mumbai. Why do we trust our most advanced, high-speed technology to a loose pile of broken rocks? Why not use solid concrete or high-strength asphalt? The answer is a masterclass in structural resilience. Today we're uncovering the engineering genius of railway ballast and its strange connection to the age of sail. To understand the stone, you must first respect the burden. A modern freight train is a rolling mountain. We are talking about tens of thousands of tons, applying surgical concentrated pressure onto the earth. If those tracks sat directly on top of the soil, the ground would behave like a liquid, swallowing the steel. This is the first job of the ballast: distribution. It takes that massive load and spreads it over a wide area. Think of it like snowshoes for a train. It prevents the infrastructure from sinking into the soft planet below. But there is a second, more dynamic challenge: vibration. A train at full speed creates a rhythmic earthquake. If the tracks were bolted to a rigid concrete slab, the constant microshocks would cause the concrete to shatter. The stone bed acts as a semi-fluid cushion. It allows the entire track structure to shift, flex, and breathe. It's a paradox. The rocks stay in place because they are loose. This flexibility is what prevents structural fatigue. Now let's talk about the geometry of the stones themselves. Have you ever noticed they are never round? Smooth stones, like those found on a beach, would be a disaster for a railway. They would act like ball bearings. Under vibration, rounded pebbles roll over each other, causing the track to slide laterally and lose its alignment. This is why engineers specify crushed stone, typically high-density granite, trap rock, or quartzite. These stones are jagged and angular. When they are packed together, their sharp edges interlock. This interlocking creates a solid, immovable mass that can withstand incredible side loading during turns. Beyond structural support, this stone bed serves as a massive 2,000-mile-long plumbing system. Water is the enemy of stability. Standing water rusts steel and turns the track foundation into weak mud. But because the ballast is full of gaps, it acts as a French drain. Rainwater flows straight through and away. This keeps the wooden sleepers dry and ensures the earth underneath remains compacted and solid. Then there is the battle against nature. Without ballast, the tracks would quickly be reclaimed by the forest. The thick layer of sharp rocks is a hostile environment. Seeds find no soil, and roots find no purchase. If vegetation were allowed to grow, the roots would hold moisture and break apart the stable foundation. But where did this system begin? The name ballast reveals a fascinating maritime history. In the era of wooden trade ships, a vessel sailing without cargo was dangerously light and prone to capsizing. To lower the center of gravity, sailors would fill the bottom of the hull with tons of heavy rocks. This weight was called ballast. When ships arrived in port to load goods, they would dump these stones on the shore. Early railway engineers, often working near major ports, looked at these discarded piles of stones and saw a solution. They used the ship's ballast to stabilize the new iron roads, and the maritime term became permanent rail vocabulary. Today, while materials are more carefully selected, the core principle remains unchanged for over 2 centuries. So next time you see those jagged rocks, remember, you're looking at an ancient solution for the modern age. This is Simple Things, Surprising Histories. If you enjoyed this journey, hit like and subscribe for more stories.